Thank you, Jamie, and thank you for the invitation. Yes, so I'm going to talk about space-time singularities, in particular, the question, what is a space-time singularity? Or really, if you want to be precise, what is it to be a singular space-time? And in fact, so this looks as a, grammatical change, but I think it actually mirrors a very, well, both a big ontological change and also a big change in the history of the course of general relativity and how it changed from the first half of the 20th century in the transition to the second half. And well, so if it's a talk in philosophy of physics and a question like this is asked very, very often, you'll encounter what might be a philosopher's favorite move, namely to quickly rephrase the question from a what is question, what is a space-time singularity, to a what are the necessary and sufficient conditions question, what are the necessary and sufficient conditions for something to be a singularity or for space-time to be singular. I call that the philosopher's favorite move because it has happened many, many times in the history of philosophy, and especially analytic philosophy, right? Start out with the question, what is knowledge? And it's turned into decades of discussion about necessary and sufficient conditions for something to be knowledge, if not hundreds of years, if you start with Plato. And, or what is truth? Questions about necessary and sufficient conditions for something to be true, and so on. And I think this is a very, I mean, it's a successful or pursuit-worthy move, but I think it also has one also has to pay a price. And in particular, with regard to the original question, what is a space-time singularity? Maybe more generally, I think it narrows the field of view to some extent, especially with regard to the history of general relativity, because I think many of the moves that relativists have tried in order to answer the original question sort of fall by the wayside, or one pays less attention to them if one reformulates the original question in this way. And I think this is emphasized by the fact that philosophers only really properly tried to answer these questions in the late 90s. And the two most important works in that regard, I think, are John Ehrman's Banks, Crunches, Whimpers, and Shrieks, and Eric Curiel's The Analysis of Singular Spacetimes. And Eric, in this paper, proposes the following schema. So he says, the commonly accepted schema for fixing a rigorous definition of a singular spacetime is spacetime m, g satisfying a particular condition is singular if and only if there exists a curve gamma incomplete in the sense that second thing to fill in. And many, quite possibly all, attempts of defining what a singular spacetime is can be brought into this schema. But the very possibility of asking or of putting forward this schema and of asking the question this way and of defining the placeholders here in this way only really becomes possible with Penrose's 1965 paper on singularities and gravitational collapse, which gives the first singularity theorem of GR, and which also provides the schema for all, or the blueprint for all subsequent singularity theorems. And the reason I'm saying that you can only really put the question in this way after Penrose 1965 is that the very idea of defining singularities, or what a singular spacetime is, via incomplete curves or incomplete geodesics originates with Penrose. And all the way up until then, that thought wasn't really present at all. What a singularity was conceptualized in a rather different way. And so that's basically my talk is going to be about this transition. So the spotlights of the previous 50 years up until 1965 and what changed then. And also one of the lessons I want to drive home, or one of the things I want to argue for, is that many of the moves that were present in the literature before 1965, before this reformulating and rephrasing, have remained fruitful in the years after 1965. And there's a sort of peaceful coexistence of this way of thinking on the one hand and of a different way of thinking on the other in the physics literature. But I think philosophers have only really picked up on this way of thinking. What are the necessary or sufficient conditions for a singular space-time? And even that, much work left to be done. Okay, so this is the Singularity Theorem from 1965. One can put it in the following form. It says that if a time-orientable spacetime fulfills the following three premises, namely, first, an energy or curvature condition, second, a causality condition, and third, an appropriate boundary condition, then it contains incomplete geodesics. That, everything that is in white here, is essentially the structure of both this Singularity Theorem and every subsequent Singularity Theorem. And the Singularity Theorem of 65 fills in these conditions in the following way, saying that local energy is non-negative, it's the energy condition, spacetime has an initial Cauchy hypersurface, and that there exists a trapped surface in the spacetime. And one thing I'm going to argue for will become quite transparent is that each of the things that I underlined here were complete innovations at the time. Up until then, all arguments that tried to argue for the existence of singularities used very particular matter models, a particular form of the energy momentum tensor, like a particular fluid. And that was strongly generalized when Penrose instead used a very general condition on the energy momentum tensor that would apply to many, many matter models rather than to a particular one. There was some work by Koma, Andrei Chadiori, that foreshadowed it, but it really was only brought to the forefront and to its full potential in Penrose's theorem. And even more game-changing was the condition of a trapped surface in spacetime, which was a completely new concept that wasn't even foreshadowed before then. And also the idea that what you're aiming for, what you're proving, is that if these conditions are fulfilled, then the spacetime contains incomplete geodesics. And it's only implicit in the Penrose paper, in the 65 paper, that from this it follows that the spacetime is singular. He never actually says it explicitly. He calls the paper Singularities and Gravitational Collapse, and then speaks about singularities in the introduction, but in the theorem itself, that final step is never made explicit. And I think this actually hints at something important, namely Penrose's own interpretation or his view on what the relationship between incomplete geodesics and singularities are. And I'm going to come back to that. But for now, my main point is that there are two camps in the community of mathematical GR, and they're to some extent separated by the Penrose 1965 paper. The first camp already starts to form basically immediately after GR is defined in 1916 or 1915. And that's a camp that treats the question of what singularities are by studying specific solution to the Einstein equations and asking themselves what a singularity in this or in that solution signifies. And to the extent that they wonder about singularities in general, it's via this exemplar strategy, looking at specific physically relevant solutions and wondering how the singularity in that solution should be interpreted. And then the second camp, I would say, really originates with 1965. And that's the camp that asks the question of what singularities are by trying to find a general definition of the term singular spacetime and the search for counterexamples to such a candidate condition. And that's, in a way, a more global strategy. You try to find a general definition of what a spacetime is and try to stay as far away as you possibly can from looking at any specific solutions. And yeah, so this starts with Penrose 1965. But the first camp did not sort of fade away or hand over. I would say starting from 1965, the two camps coexist. And you can also have this one and the same person sometimes having camp 1 hat on and sometimes having a camp 2 hat on. So even today, I think this strategy is often pursued. And it has its own advantages compared to the second strategy that asks for definitions and or necessary and sufficient conditions, specifically because it's much more focused on the solutions to the Einstein equations that have an immediate application in physics, rather than to the whole solution space of the Einstein equations, of which we know that only a very, very small part relates to our universe. Okay, so here's how I'm going to proceed. I'm first going to start at the very beginning, namely at Einstein's and Schwarzschild's interpretation of the very first exact solution to the Einstein equations, Schwarzschild solution of 1916, and how they interpreted the two singularities that appear in that Schwarzschild solution. Then I'm going to talk about the 1923 conference in Paris, where the second singularity, the Schwarzschild Singularity or Spherical Singularity, takes center stage and the discussion of how it should be interpreted. And then go to Eddington's interpretation of especially the second singularity in the Schwarzschild solution. From there, then I'll move on to the late 30s. So you see, this is not a careful piece-by-piece reconstruction of the whole history, but spotlight here, spotlight there, and trying to see red threads. So jumping to 1939 with Oppenheimer's and Snyder's paper that used the Schwarzschild solution as a model not of a static star, but of a collapsing star, and used a particular model, including a matter source, to represent or describe gravitational collapse. And here, just like in the Paris conference in 1923, the question arises whether singularities could possibly come into existence in nature. And I'm going to talk very briefly about Wheeler's struggle with the Oppenheimer-Snyder analysis and his argument that it can't be the end of the story, and then move on to Finkelstein's interpretation of the second singularity, what many people call the Schwarzschild singularity, which only in the late 1950s is reconceptualized as an event horizon. I'm going to describe how it came to that, and also why I think some of the narrative that has been present both in the philosophical and in the historical literature that allegedly it was also puzzling that people didn't get that the Schwarzschild singularity wasn't a real singularity, that this is a bit too fast, and that there really was, it wasn't just that somebody didn't get it. You really needed a new way of thinking in order to think of event horizons. And then from there, I'm going to move to Penrose's path towards the first Singularity Theorem of 1965, for which Finkelstein's paper played a major role, probably the most important role, and then compare Penrose's path with Lifshitz and Kalatnikov's arguments against Oppenheimer-Snyder, and come to Penrose's breakthrough in 1965. And while I'm going through this history, so the structure of the talk, as you can see, is given by the history, but in between, I'm going to distinguish different interpretational moves that are made by different protagonists, different possible ways of interpreting singularities. And towards the very end, I'm then going to come back and summarize all these interpretational moves and ask which of them are still doable today and which of them we cannot use anymore. Okay, so first to the Schwarzschild solution and the two kinds of singularities that appear in it. Okay, so as you all know, Einstein found the Einstein field equations in November 1915, which link gravity or space-time curvature with the mass energy of matter. And every solution to these equations, so here the full Einstein equations with a mass energy tensor as a source term, and here the vacuum equations for pure gravitational fields. And every solution to these equations represents a universe or a part of the universe that is possible according to GR. That's a way of thinking about the solution space. And some of these solutions have singularities. Now, a question that is going to be important is whether this means, the fact that they have singularities, whether this means that singularities are possible, even generic in nature, or whether this means something different. And, one could conceptualize this by distinguishing between a literal and a careful version of scientific realism. A literal interpretation of a given solution would say, well, if this solution describes the real world or a subsystem of the world and it features a singularity, then clearly singularity must appear in nature, or the theory is wrong. That would be the literal way of interpreting it. Careful way is well, careful, different way for slow, trying to deliberate whether there are other possibilities. Okay, so to the history. Einstein in November 1915, actually before he found the final field equations, started to, just a week before, started to look at Mercury's perihelion around the sun and tried to correct the Newtonian account of it. So he tried to find a solution to the linearized vacuum equations, which fortunately were the same in the previous iteration as in the final field equation. So the vacuum equations were correct. And so he tried to find a solution that would be able to model the sun, or rather the exterior gravitational field of the sun. And he assumed that the gravitational field would be spherically symmetric, static, and asymptotically flat. Those were the three conditions. And he found an approximate solution, and using that approximate solution, managed to calculate the perihelion of Mercury and find correction terms to the Newtonian prediction, which exactly fit the observations. Then just a few months later, Schwarzschild found the exact counterpart to Einstein's 1915 approximate solution, right? Schwarzschild took the same premises that Einstein had, static, spherically symmetric, and asymptotically flat, and found an exact solution to the vacuum Einstein equations. And here you see it not in Schwarzschild's, but in Drosta's coordinates, which have become much more guiding. And here you quite quickly see that there are two singularities in the Schwarzschild solution. Here, if so r is the radius, or approximately the radius. And if r is 0, then this term becomes singular, so diverges. And if r is equal to 2m, where m is interpreted as the mass of the sun, then this component of the metric tensor becomes 0. So there's two singularities. Singularities here interpreted as a region in space-time where one or more component of the metric tends towards infinity. And so two singularities, one, the central singularity at r equals 0, and one, the spherical singularity at r equals 2m. And now both Einstein, so the central singularity also appeared in Einstein's original approximate solution, and it reappeared in Schwarzschild's exact counterpart. And the central singularity didn't really bother either Einstein or Schwarzschild. They were not surprised by this, and nor should they have, because this was a very, very common phenomenon. They were used from electrodynamics. If you use vacuum electrodynamics and you ask, well, what's the not introducing any modeling of the sources, not introducing any charges, and you look just at the exterior field of, the exterior electric field of an electron, then that electric field tends to infinity at the point where the electron is actually located. And everybody interpreted this kind of singularity as a kind of a placeholder for the charge that was not included in the model. So it wasn't interpreted realistically, it was seen as a placeholder for the material system that had not been included in the model, because you just looked at the exterior field. And so when you then go to R2E0, I equals 0, the field diverges. The spherical singularity was more of a surprise because nothing like that was known from electrodynamics. And one might have worried about it quite a bit, and as we're going to see, people did worry about it in the 1920s, but many people quickly agreed, well, it's just an artifact, just like the center singularity, because when you calculate where the spherical singularity would be, given that it depends on the mass of a body, you quickly find that for any realistic star, as people thought of it then, it would always be deep inside the star. So it would never appear outside of the star. It's a mathematical artifact, again, produced by the fact that the material source wasn't actually included in the modeling. Okay. Now, so these are the two interpretations I want to distinguish first. So first is Einstein's and Schwarzschild's interpretation of the central singularity of the Schwarzschild solution, which I call the placeholder interpretation, which says that the singularity is nothing to worry about, but something to be expected. It is an artifact of the fact that the source of the gravitational field has not been included in the modeling process, and thus the singularity is a placeholder for a model of the matter source not yet delivered. And the interpretation of the spherical singularity, or the Schwarzschild singularity as it was often called, which Eisenstedt attributed to basically everybody in the 1910s and 1920s, Einstein, Schwarzschild, Weil, Eddington, here I'm not so sure. Eisenstedt called the pragmatic interpretation of the spherical singularity, which says that the singularity is a mathematical artifact, something that could not correspond to anything in nature, and it's not physically relevant. And thus, here's the extra kicker, we should restrict the coordinates such that the coordinate system only starts at r more than 2m. And this makes sense as a modeling assumption, and in fact also for applications, right? So when Schwarzschild and Einstein wanted to derive the perihelion of Mercury, they didn't need to know anything about the sun, about the interior of the sun, what it's made up of, and how its surface looks like. They just needed to know the exterior gravitational field that Mercury is subject to. So in order to not cause any trouble in the calculations, it made absolute sense to cut the coordinate system off at I equals to m and only bother with the regular solution outside where you don't have any singularities. Okay. Now, this pragmatic interpretation of the spherical singularity was challenged or got under pressure for the first time at the conference at the Collège de France in Paris in April 1922. So here, Einstein was there for a series of lectures, and we only have lecture notes from an attendee, from Alfred Nordmann, and only in French. So we don't know all the details, not nearly all the details of what happened here, but you can see Einstein. This is a picture of one of the lectures, and you see Einstein here looking at something that looks as if one might be a star and the other its gravitational radius, as I just drew it, or the other way around. Because on the 5th of April, 1922, Jacques Hadamard, a great French mathematician, asked Einstein, what if a star were to be so massive that its spherical singularity ended up outside of the star? And Einstein's answer was, this would be a catastrophe for the theory. And he went away and thought about it, came back the next or 2 days later, and made the following argument, as reported by Nordmann. He said, Hadamard's catastrophe will never, ever happen. I've calculated that before a star could accumulate sufficient mass to be entirely contained within its own Schwarzschild radius, so the r equals to m, the pressure at the center of the star would become infinite. Under such conditions, clocks would not run, and thus time would stop, preventing the Hadamard catastrophe from ever developing, since nothing develops without time. I'm paraphrasing here. But so this argument up until here is actually already contained in Schwarzschild's second paper of 1916, in which he gives the so-called interior Schwarzschild solution. Right? The exterior Schwarzschild solution was supposed to model the exterior gravitational field of the sun. And then in the second paper of 1916, he gave the interior matter source that produces this exterior. And it was a particular model of a star, of a fluid ball with pressure. And in that second paper of Schwarzschild of 1916, he already predicted that the pressure at the center of the star would become infinite. This addition here is by Einstein, though. Okay, Hadamard was satisfied with this answer, and so for quite a while that was it, right? Nobody worried that much what would happen if the spherical singularity would end up outside of a star, and what would that mean? But why would it have been a catastrophe in the first place? Why was Einstein not worried about such a singularity if it's inside a star, but was worried about it when it would have ended up outside of the star? Well, I think Einstein regarded general relativity as what I would call a hybrid theory, a theory that is fundamentally correct with regard to space-time regions containing only gravitational fields. So if you want, in the domain that is described by the vacuum Einstein equations, and only phenomenologically correct with regard to space-time regions in which matter is present. The energy momentum tensor in GR was only a placeholder for an adequate quantum theory of matter not yet found, not something that adequately represents nature. So Einstein was fine with introducing singularities to stand in for matter, for the proper quantum matter, just meant switching one placeholder, the energy momentum tensor or material system described as a fluid ball by the energy momentum tensor, for another. One placeholder is switched for another. So that's okay. You don't have to take either the energy momentum tensor or the singularity that stands in for matter seriously. But if singularities were not supposed to actually appear in nature, and they were not supposed to appear in vacuum regions, because that was supposed to be the regions where general relativity was supposed to be exactly correct, not just approximately correct. And so if singularities appeared in regions where matter is not present, then that would be a real challenge to the theory. And that's what was at stake in the debate with Hadamard. Okay, here are a few, so despite these arguments and despite people thinking that the Schwarzschild singularity was a mathematical artifact, it still seemed to have driven, made people think. And here are, there was a real cottage industry of people introducing ever new terms, names for the spherical singularity in the Schwarzschild solution. Eddington wrote in 1920, there is a magic circle which no measurement can bring us inside. It is not unnatural that we should picture something obstructing our closer approach and say that a particle of matter is filling up the interior. And other names for the spherical singularity that were introduced during the 1920s were the discontinuity, Schwarzschild's own name, the barrier, Kotler, the sphere or the gravitational radius, as Weyer said, the hole in the world, the singular frontier, the catastrophic frontier, the limit circle, or the death. This is the Nordmann who took the notes at the Paris meeting. And this is something that an accident that I quite like is that Schwarzschild's name, if you translate it into German, would mean black shield. And so given that so many here gave names that made the Schwarzschild, the spherical singularity look like a singularity, it's quite striking that the person who discovered it has the name black shield. And it's even more prophetic because, of course, that spherical singularity would later be reinterpreted as the event horizon of black holes. Okay, so here's a third interpretation, specifically for the spherical singularity of the Schwarzschild solution that was proposed during the 1920s, which one might call the barrier interpretation, which says that the singularity is a kind of barrier through which a material system, like a particle or an observer, cannot pass. This barrier might be the surface of an extended material body, in which case the barrier interpretation goes over into the placeholder interpretation. But it's interesting. So why did people think that it might be kind of barrier? Well, it's because if the metric becomes singular, then it's impossible to describe motion through that region, right? Because, and it looks as if you can't get through because the metric is not well defined in that sphere or at that surface. And so I think that's how the idea that it might be a kind of barrier originated. Now, I want to look at Eddington in a bit more detail, partly because he seems to struggle with the right interpretation, and we have a bit more detail of how he thought about it, and also because something he did became crucial in the second phase, in the phase after the 1950s, namely discovering a new coordinate system that was later rediscovered by Finkelstein. I want to quickly speak about how all this is related. So in the quote above from 1920, we saw Eddington call the spherical singularity of the Schwarzschild solution a magic circle. But we have to be careful because the quote is taken from Eddington's semi-popular book, and the context in which it appears shows that he thought of the barrier as an indicator that there is a material source, or in the case of the spherical singularity, the surface of a material source hidden in the solution. And this is actually a move that is very similar to something that Einstein did in his debate with de Sitter in 1917. So I originally had a couple of slides on the de Sitter solution, but then decided I had to take them out for reasons of time. But the de Sitter solution is the first solution that was found for the modified Einstein equations with cosmological constant. And de Sitter thought of it as a vacuum solution and argued that it was a vacuum solution, and that hence the modified field equations also didn't fulfill Mach's principle. But Einstein found that there was a singularity at the horizon. So it was like a cylinder like this, and had a horizon, and there was a singularity at the horizon. And Einstein said, well, the singularities there at the horizon, those are indicators of masses. Where these singularities are, this is where masses are, or where masses should be thought of. They're not properly modeled yet, but the singularities indicate the presence of masses. And similarly, in Eddington's 1923 technical textbook, Eddington discussed both the singularities appearing in the de Sitter solution and in the Schwarzschild solution, thinking about what singularities may or may not indicate. And so here's a quote. I have to move this. Let's look at this here at first. So he says, a further question has been raised. Is de Sitter's world really empty? There is a singularity at r equals this, similar to the singularity at r equals 2m in the solution for a particle of matter, i.e. the Schwarzschild solution. Must we not suppose that the former singularity in the de Sitter solution also indicates, i.e. just like in the Schwarzschild solution, also indicates matter, a mass horizon or ring of peripheral matter necessary in order to distend the empty region within. So there you, quite explicitly, singularities are interpreted as indicating the presence of matter. And second, but he struggles with it. He thinks this kind of indicator interpretation he's not quite comfortable with either. He says a singularity in the metric does not necessarily indicate material particles, for we can introduce or remove such singularities by making transformations of coordinates. And so he comes very close, and for example, Jean Eisenstadt has asked why he was so close. Why is he not making the distinction between coordinate singularities and real singularities here? Well, he seems to think that, and in fact, it does often happen. I think it's not a misunderstanding on Eddington's part. He's aware that transforming away a singularity by changing the coordinate system only really means something if you can be sure that the singularity doesn't pop up somewhere else in the new coordinate system. And so that's what he speaks of down here. Okay, so, but it's interesting that in Eddington 1924, a year after this textbook, Eddington would introduce exactly such a coordinate system for the Schwarzschild metric, namely one that transforms away the spherical singularity without a singularity popping up elsewhere. But he doesn't comment on it. The paper is on a comparison between GR and Whitehead's theory, and he doesn't comment that this is what his new coordinate system actually does. So either he did not realize that he had transformed away the spherical singularity, or he was unsure that this had not led to another singularity elsewhere in the space-time. So exactly this scenario that he describes here. Okay, we're going to come back to this. Okay, so this brings me to what I want to call the indicator interpretation, which we find both in Schwarzschild and Einstein, both in Eddington's interpretation of Schwarzschild solution and in Einstein's interpretation of de Sitter's solution, and which I will argue is still a popular move in the discussion of exact solutions today. If you look at the exact solutions literature from today, and when people try to interpret a given exact solution, they often interpret the presence of singularities, especially localizable or semi-localizable singularities, curvature singularities, as indicators for the presence of matter that has not been included into the solution yet. So it's at the first sight, it looks very similar to the placeholder interpretation, but the context of discovery or the context of application is slightly different. So you have to imagine that very often the scenario is that we just found a new mathematical solution, like the de Sitter solution to the gravitational field equations, and there's a singularity in this solution, and we then interpret this, the presence of the singularity as an indicator for the presence of matter sources that gives rise to the gravitational field. That is the solution that we just found. And I think it's important that indicator should not be interpreted as sufficient condition for, because, well, there are solutions in which you have, well, I'll come back to this. I think it's a much weaker condition. Being the indicator for something is not the same as being a sufficient condition for something. So basically, it's a reason to look for material sources. It's a reason to do exactly what Schwarzschild did, right? He had the exterior Schwarzschild solution first, and then he thought, there's the singularity there. I have to, and it was supposed to be a model of the sun anyway, a proper description of the system would include a material source and would have to be there where the singularity is. And then he found the interior Schwarzschild solution. And so finding a singularity in this way can be taken as a sign of pursuit worthiness to looking for an extended solution that includes a model of the matter that gives rise to the vacuum solution that you just found. In fact, even Roy Kerr, when he found the solution, the exact solution to the vacuum equations that we now interpret as giving us the description of rotating black holes, always said, well, we really should try to find an interior solution. And even thinking about black holes today, well, it's a collapsed star. So in the interior of the black hole, there is an awful lot of matter. So you could, at least for Schwarzschild and Kerr black holes, it still seems to be a viable move. Okay, now next part of the story brings us to, yeah?
Just a very quick question on this. Is there a rotating solution that's known for the interior of a body?
No, there's no, so the counterpart of the interior Schwarzschild solution that would sort of match up to the exterior Schwarzschild solution, there's nothing like that for Kerr. But Kerr always wanted it, and but nobody ever found it. Yeah. So far. Okay, so next part of the story. I mean, a lot of what I said here was interpreting the mathematics that had been found, right? I mean, here the only direct application to physics was in Einstein and Schwarzschild's original description of the gravitational field of the sun and the calculation of perihelion Mercury from it. Now, I'm going to speed up a little bit here. This changed when in 1939, Oppenheimer and Snyder gave a dynamical picture using the Schwarzschild solution in trying to model the gravitational collapse of a star. And what was crucial about what happened here is, in a sense, similar to the kind of thing that Einstein was afraid about the Hadamard catastrophe. Something similar happened here. Namely, Oppenheimer and Schneider showed that as a result of such a collapse, you start out with a star, everything nice, everything regular, it collapses and collapses and collapses, and a central singularity comes into existence as a result of that collapse, because it becomes ever closer to the vacuum Schwarzschild solution as a result of the collapse. And now one might ask, so given this argument of Oppenheimer and Schneider, did they falsify Einstein's reasoning of 1922, which was supposed to, well, stop a star from becoming so dense that the spherical singularity ends up outside of the star, let alone a central singularity forming? I think the answer is quite directly no, because Oppenheimer and Schneider made idealizing assumptions, namely in particular the one that the pressure inside the star vanishes. So the energy momentum tensor that they used to model the star had no pressure terms, whereas for Einstein, just like in the interior Schwarzschild solution, the assumption of non-vanishing pressure played a major role. So Oppenheimer's and Schneider's analysis rests on two very specific assumptions: that the gravitational field of the collapsing star is exactly spherically symmetric, and that the matter that the star is made of can be idealized as pressureless dust. And Penrose would show that the major results of Oppenheimer and Schneider, namely that of continuing collapse and that of a formation of a central singularity, do not depend on these assumptions, but that would take another 25 years. Now, John Wheeler engaged very strongly with the analysis of Oppenheimer and Schneider. And in fact, in a way, it was his entry point into general relativity, because Oppenheimer's and Schneider's paper really connected nuclear physics, the modeling of the star, and general relativity, the description of gravitational collapse. And Wheeler was a nuclear physicist, and he was very unhappy with the modeling of the star by Oppenheimer and Schneider, and thought it was a very unrealistic model of the star and of how it would collapse. And so he spent years using some of the first supercomputers with some of his postdocs and PhD students to try to come up with a better model of the star itself, and investigate whether, if a more realistic model of the star is used, you would still get a formation of a central singularity and a continuing collapse, or whether you would find a new equilibrium situation. So Wheeler's interpretation of the central singularity in this Schwarzschild solution, as it appears in the Oppenheimer-Schneider collapse model, I want to call the problem interpretation. He believed that the presence of a singularity in that solution or in that model is a sign of a problem. The theory is inadequate, or at least incomplete. The model that brings about such a singularity needs to be replaced by something better. And that's a much more radical change than just filling in a placeholder like Schwarzschild did, right? Nothing had to be changed about the exterior Schwarzschild solution or about the theory in order for him to fit it to the material source. So Wheeler thought you really have to change the complete model. And the presence of singularities is, you could also call it a breakdown interpretation. The presence of a singularity is a signifier of a fundamental problem and the need for fundamental change. Okay, so next important step. So now this is already in the mid-1950s. And one thing that I haven't emphasized very much yet is that even though quite a few people, in particular Eddington, Lemaitre, Robertson, had found coordinate systems of the Schwarzschild solution, in which the r equals to m region is not singular, nobody had yet sort of reconceptualized what this meant. Nobody had really thought this through to the end. And I think it's really not just about the distinction between coordinate singularities and real singularities, because when Finkelstein rediscovered Eddington's coordinate system, he needed a completely new interpretation and move. And he gave an argument which established, here's the abstract of his 1958 paper, that the Schwarzschild surface r equals to m is not a singularity, but acts as a perfect unidirectional membrane. Causal influences can cross it, but only in one direction. And so this is a very, clearly a separate move from just transforming away and seeing something was a coordinate singularity. What Finkelstein realized was not only that I equals to m is not a singularity, he also realized something else, namely that it is something else, what he called a unidirectional membrane, and which would later be called an event horizon. And Finkelstein's path towards this way of thinking was brought about by him finding the same coordinate system Eddington had, where I equals to m is not singular. B, focusing on the behavior of null rays. Nobody had really done that so far, and I think this is really a crucial ingredient. And him thinking about how the solution behaves under time reversal transformations. And I think that essentially what Finkelstein showed is not only this coordinate system, which is what the paper is mostly cited for, but also the idea of an event horizon, and he found the dichotomy between what would later be called black holes and white holes. It's clearly, I believe, quite clearly in the paper. Okay, now, so Finkelstein's interpretation of the spherical singularity of the Schwarzschild solution, I might call a transformative interpretation, that says that the spherical singularity of the Schwarzschild solution was actually something else in disguise, a membrane that can be passed from one side of the sphere, but not from the other. Okay, this brings me to the final section, because this realization of Finkelstein played a major role, quite possibly the most important role, for Penrose to come to the first singularity theorem. And Rindler, so I put Rindler here because Finkelstein came up with the idea of thinking of I equals to m as not a singularity, but a unidirectional membrane. And Rindler generalized this and introduced the name event horizon in the same year already, 1958 paper. And both papers had strong influences on Penrose, or at least the ideas of both men had strong influences on Penrose. So here is a quote from an interview with Penrose, where he describes how he went to a lecture by Finkelstein in 1958, so the same year in which the paper that I just showed you was published. And it was at King's College London, and Penrose was a research fellow in Cambridge at the time, so it was just a short train ride. And so he describes the following: I remember being struck by the fact that although you remove the apparent singularity at r equals to m, the horizon of the black hole, using later terms now, you still had another singularity at r equals 0, the central singularity. It seemed that you just pushed the problem somewhere else. When I got back to Cambridge, knowing very little about general relativity, I started to try and prove that singularities were inevitable. It seemed to me that maybe this was a general feature, that you couldn't get rid of the singularity. I really had no means of proving this at the time. So this is now 7 years before he finds the singularity theorem. And in between, and he worked, it was the start of Penrose entering general relativity proper and really changing his focus of work and working on general relativity. And he spent years first working out a spinor formulation of GR. And in other interviews, he also described, well, he asked himself, so how could he approach this? And he said, well, one of the things that I felt I knew well and that not many other people knew well were spinors. And so he set himself to trying to think of GR in spinorial terms. And first by himself and then together with Newman, rewrote GR in spinor terms, and which eventually would be used in the 1965 theorem. But in between, the Russian school of relativity pushed in a different direction, also engaging with the Oppenheimer-Snyder analysis, just like Wheeler had. Lifshitz and Kalatnikov, I also brought Selovich here because he was the guiding light of the Russian school, but Lifshitz and Kalatnikov argued that you can get rid of the singularity that arises in the Oppenheimer-Snyder collapse, the central singularity, if you drop the assumption of the spherical symmetry of the collapsing body. So this made precise the feeling that many had already had up until then, namely that the formation of a singularity predicted by the Oppenheimer-Snyder collapse was an artifact specifically of the highly idealized assumption that the collapsing body is perfectly spherically symmetric. And they said, well, no actual star is perfectly spherically symmetric. And quite possibly, if you can give an analysis of a collapsing body that does not rely on this, maybe then you won't have a singularity. And they wrote a paper in which they argued for exactly that. Penrose read that paper and found himself not convinced. And at the same time, at roughly the same time when this paper came out, and Penrose must have read it sometime between 1963 and 1965 because he cites it, just like the Oppenheimer-Snyder paper and Wheeler's engagement with the Oppenheimer-Snyder paper. In the same year, the whole thing moved from being an issue mostly of mathematical relativity to something that might possibly have really something to do with heavenly bodies that we see at the night sky, because Schmidt, after receiving data from Hazard, Mackey, and Schimmins, this is Fowler, in Nature announced the discovery of quasars, which are by far the most energetic bodies on the night sky. But it took so long to observe them because they only radiate in the radio spectrum. So you needed radio telescopes to find them. But so Hoyle and Fowler gave the mathematical analysis and models of quasars, and they said our present opinion is that only through the contraction of a mass of 10 to the power of 7 or 10 to the power of 8 of the mass of the sun to the relativity limit can the energies of the strongest sources be obtained. So suddenly there was the idea of incredibly massive bodies that were collapsing and that would give rise to quasars. And this development, on the one hand, the development of quasars and the newest developments in mathematical relativity together were discussed at the 1963 Texas conference, which brought together for the first time mathematical relativists and astrophysicists. Here is one of the photos from the time of quasar, the lightest, most energetic quasar on the night sky, 3C273. From back then, here's a Hubble photo from just a few years ago, of course, much clearer. Okay, so this also, I think this was a second, it was clearly a second major influence for Penrose to think back to the ideas that he had had after Finkelstein's lecture in 1958, because suddenly not only were people talking about gravitational collapse again, but also there was the mathematical relativity argument that the singularity, the I=0 singularity that he worried and wondered about after Finkelstein's lecture would not actually appear as a result of gravitational collapse. Whereas his original intuition was that maybe it would be generic, maybe that there was nothing you could do to make it disappear, including getting rid of spherical symmetry. He had the original intuition that none of this would help and that these singularities would be generic. At least that's how he remembers it, decades later. Okay, so this brings us back to the Singularity Theorem of 1958. And again, so this premise, as I said, was crucially new. All the previous models had very specific meta models of collapsing bodies, just like, say, the Oppenheimer-Snyder model was a fluid ball with no pressure. Crucial ingredient was the new idea of a trapped surface that I can't go into now. And also completely new and easily overlooked because it has become so prevalent everywhere in every subsequent analysis, is the idea not to look at the components of which tensor diverge or do not diverge, but instead to look at geodesics and whether geodesics are incomplete or not. Incomplete in a rough sense, meaning they just stop somewhere rather than going on. Okay, but now what do incomplete geodesics have to do with singularities? And I think that's a subtle question in interpreting Penrose's papers from the late 1960s. In the 65 paper, he points out that the central singularity in the Schwarzschild solution is a physical singularity, and commenting on his theorem 4 years later, he writes, "We know that there must be some spacetime singularity resulting inside the collapsed region. However, we do not know anything about the detailed nature of this singularity." And so this does not sound as if Penrose just identified geodesic incompleteness with there being a singularity. And I think rather that he took geodesic incompleteness as an indicator for there to be a singularity, a semi-local singularity, that which causes the geodesic incompleteness. The reason that the geodesic is incomplete, that it just stops, is because it ran into a singularity. Okay, so I think Penrose's interpretation, at least in the late 60s, is a mixture of the following two. The first, I would call the indicator interpretation 2.0, that says that geodesic incompleteness is an indicator for the presence of a physical semi-localizable singularity. Again, indicator does not mean sufficient condition, because as Eric showed in the 1999 paper, that's not the case. It's not the case that every geodesically incomplete spacetime has a semi-localizable singularity, like a curvature singularity or a region where the components of the metric tensor diverge. It's not a sufficient condition, but it's maybe a reason to look for something like that. And this, the second part is a barrier interpretation 2.0. The physical singularity is a kind of barrier which brings geodesics to a premature end, i.e. makes the geodesics be incomplete, right? The moment when the geodesics are incomplete, it's almost as if they ran into a barrier, but now a barrier of a very different kind. Okay, now just to sum up. So one thing that is, I think, a bit ironic is that if you remember Schwarzschild's and Einstein's engagement with the Schwarzschild solution in 1916 and in the 1920s, if they were worried about anything, it was about the spherical singularity. That was a bit weird. That hadn't really been had not really appeared before. You couldn't think of it as a placeholder as straightforwardly as about the central singularity, and had no counterpart in electromagnetic theory. And Penrose's singularity, Finkelstein showed that this is not really a singularity after all, but what we today call an event horizon. And Penrose showed that the thing that was the real danger, coming back to Wheeler problem interpretation, the real challenge is the central singularity in the Schwarzschild solution. Okay, to sum up, here's a quote from Griffith and Podolsky from 2009. It appears that it is much easier to find a new solution of Einstein's equations than it is to understand it. And I think it's clearly true, given that even the most simple solution to the Einstein equations, the Schwarzschild solution, was completely re-understood 50 years after it was first discovered. I think the different interpretations of singularities that we encountered being used by relativists are somewhat orthogonal to the question of how a singularity or a singular spacetime is defined, because they're instead about how the discovery of a singularity in a given solution is used. And just final thing, which of these interpretations are still useful today? I'll just quickly go through them again. So we have the placeholder interpretation. A singularity is nothing to worry about, but something to be expected, an artifact that is just a placeholder for a material model that has not yet been included in the process. I think you can still say that, right? You can still use that. You can still use the Schwarzschild, the exterior Schwarzschild metric, in exactly the same way as Einstein and Schwarzschild did to model the exterior gravitational field of stars and indeed of black holes, and think that in order to properly describe the source system, you need to fill in the hole that is given by the placeholder. The pragmatic interpretation of the Schwarzschild or of the spherical solution that Eisenstedt attributed to most people in the 1920s, that is not quite available anymore. You could still make that move if you say, well, all I need to know is the exterior gravitational field of something, and you just cut off the coordinate system at the event horizon. But still, what we have learned, especially through Finkelstein, is that it's not really a singularity at all. And it's not a mathematical artifact either. It is something else, not a singularity, but an event horizon. Then the barrier interpretation can't stand for the same reason, at least as an interpretation of the R equals to M singularity, because we found, well, it's not a singularity as an event horizon. What can stand is barrier interpretation 2.0. If you're not happy with the general definition, or if you think there is more to be said than to define what a singular spacetime is, that just says a singular spacetime is one that has incomplete geodesics. If you want to ask, well, but what makes the geodesics incomplete, then you can still use this barrier interpretation. But you can only do it for some, right? Not every singular spacetime has a localizable or semi-localizable singularity, but every spacetime with a semi-localizable singularity is a singular spacetime. So the notion singular spacetime is more general than the notion of a spacetime that has a singularity. Okay, finally, problem interpretation still clearly stands and motivates that people say singularities at the center of black holes suggest that we need a theory of quantum gravity that would get rid of these singularities. And finally, last slide, the transformative interpretation that still stands. The spherical singularity has turned out to be something else in disguise, namely an event horizon. One could also more generally ask, could we ask this more generally? If we have a new solution, a singularity appears, could it be sometimes that it is something else in disguise? Maybe it's not enough to ask, is this a coordinate singularity or not? Because even if it is just a coordinate singularity, maybe it points at other, quite possibly global features of the spacetime that cannot just be captured by transforming away the apparent singularity. Finally, the two indicator interpretations here was the one that I just spoke about, of Penrose. But I also think, I just want to finish with this, that the first indicator interpretation is still very much present in the theoretical relativity, mathematical relativity community, especially that part of the community that works primarily with specific exact solutions. Namely, you have a new solution, you found it, you don't know what it means. The solution has some singularities or a singularity, and the move to think, maybe this singularity is an indicator for a material source, and I just have to now try to find counterpart of an interior solution. That is still very much being done and has often been a successful move. Okay, thank you.
Oops. Well, thank you very much. That was a really wonderful talk. I enjoyed it immensely. We've got lots of questions. I'm going to let Martin go first because he needs to rush away.
Hi, Dennis. Thank you very much for a lovely talk. Unfortunately, I have to go pretty soon, so I won't be able to join for all of the discussion session. I'm really sorry about that. Okay. But I wanted to put forward to you, I mean, I learned so much from your talk. Thank you so much. Let me maybe offer one point of view from the modern mathematical community interested in general relativity as a theory of classical physics, of partial differential equations. So in that community, in the current community, there is, you know, it's obviously very well known since already the 60s that geodesic incompleteness is something which is to be expected quite generically, but it does not capture the sense of singular space-time that, for instance, you get in the Schwarzschild solution. And of course, this is something you made clear. But I think today what counts as singular for the mathematician studying GR is something or other that happens in the course of dynamical evolution that creates such an extreme region of space-time that one cannot somehow embed the region of interest into a larger space-time such that the field equations continue to make sense everywhere in that extension.
Yeah.
So what, and because, and as you know, what that leads to is not just a single definition of what it means to be singular, but rather a spectrum of definitions and a whole list of different types of singularities you could get. So for instance, some of them could be inextendable in a certain regularity class, others could be inextendable in another sense. So I think the definition that mathematicians use now, or the idea they have, is that whatever is happening with the field equations and with the dynamics of the gravitational, it's leading to some region of extreme gravity, whatever that means. And depending on how extreme that region is, the possibility of kind of making sense of the Einstein field equations in that region breaks down, and it breaks down to various degrees. So I think geodesic incompleteness is just so coarse an idea, and it fails so strongly to track the properties of the gravitational field, that thinking of singularities in the gravitational field as in some way being captured by whether or not there's some incompleteness is not actually what people think about or think of nowadays, because the PDE point of view has just so strongly championed.
That's interesting. So that's, I mean, especially the last part that you said, that's not, so I felt myself nodding along and agreeing with everything you said, and this last part was new to me, and primarily because, I've really only studied up until 1969 maybe, and even there, right, the 1910s and 20s much more carefully than the later stuff. So so you would say that the claim von Eric's paper, that the post-1965 stuff, right, which I thought of as complementing to what I spoke about, right? I spoke mostly of until 1965, and then Eric's paper, and I think also Ehrman's book, basically argue that for this schema, right, that singularity, well, the singulariness of spacetime, singular spacetimes are redefined via geodesic incompleteness. And that's the common thread all the way since then. And so you're saying that's not true anymore, or at least not since as of the last 20 years. So it's a third step. So the two camps that I distinguished were, and I think they are not mutually exclusive, but complementing each other, right? The people who work primarily on specific exact solutions in which you have singularities like the Schwarzschild singularity, which is quite, a curvature singularity, localizable or semi-localizable in the sense that you know where the singularity is in that spacetime, at least in what region it is, if not at which point. And then the emergence of the concept of a singular spacetime, much more general, in a way much less demanding, right? So that not every singular spacetime has a singularity as in the previously discussed solutions. And now you're saying there's, in a sense, a third step that goes, well, they may still call it a singular spacetime, but now they have moved away from geodesic incompleteness as the criterion that you would give for a singular spacetime. And would that have happened only in the last 20 years, or?
Right. So Eric's, the schema and Ehrman, that's a totally valid and valuable way to start talking about singularities in general relativity, to talk about what kinds of singularities occur. That's absolutely fair, and there's lots of rich, interesting things you can ask there. What I'm saying is that the main question now of mathematical general relativity is understanding to what extent what's the nature of singularities that are expected to occur in a dynamical evolution. And for that purpose, merely thinking of geodesic incompleteness is completely missing the point, because the what's understood as singular is how can we extend solutions, and in what regularity can we extend the solutions? In what sense can we make sense of the Einstein equations in these low regularity regions? And in what sense can we still think of dynamics as making sense in these singular regions, right? That's it. It becomes a question essentially of what can we say about the regions we can extend beyond maybe some C2 geodesic incompleteness. So unfortunately, geodesic incompleteness just doesn't track the behavior, the PDE behavior of the gravitational field. So in the point of view, in the modern point of view that PDEs rule over what we think of as the dynamical sector of GR, then yeah, geodesic incompleteness is just it's not a sufficiently, it's not a sufficiently precise way of understanding what's going on in these strong gravity regions. That doesn't mean that there's a ton of interesting open rich questions to be asked about space-times as Lorentzian manifolds and the kinds of geodesic incompleteness that can occur and how they balance and etc. But yeah, I would argue that if you go to Princeton and you say Penrose's singularity theorem, people will chuck you out of the room and they will tell you, no, it's an incompleteness theorem, nothing to do with singularities.
In fact, he himself.
I'm saying that as a joke, but I'm kind of serious.
Yeah. Well, in fact, I remember him saying at some point that it really is an incompleteness theorem. It shows, and I mean that's really, I think I hinted at this. He's not really, even though he called the paper Singularities and Gravitational Collapse, he's not really talking much about singularities or singular behavior, right? It's all about whether the geodesics are incomplete or not, and then he leaves it there. He doesn't really, even though he mentions this in the introduction, singularities, he doesn't, after he gives the proof, he doesn't circle back to what the geodesic incompleteness means for the question of singularities, at least not explicitly. Yeah, so I think maybe he wouldn't be all that unsympathetic to this. But so one thing, I guess you have to go another, but one thing that I would like to know, given that they're still speaking of singular spacetimes, but moving away from the geodesic incompleteness theorem, there must still be a connection, right? Because otherwise they would have just chosen a completely different name for these properties of spacetimes, right?
Yeah, and understanding that connection is essentially the great main challenge of what's going on right now, and understanding that connection is the question, and it's going to keep people busy for another 20-30 years. I mean, there's so much to know and so much unknown about how this connection works out in practice.
Great, thank you.
Okay, well, I think next up we have Eric.
Well, wow, there's so much to say. Dennis, thank you. Martin, thank you for that extended commentary. That was great. But Dennis, that was really a beautiful paper. This God is so rich. I have so many comments and questions. Crap. Okay. I'm going to make several very short comments and then ask a question. And I promise all the comments are very short. So, in fact, to the best of my knowledge, Penrose was not the first one to mention incompleteness as a indicator or condition for singularities. That was actually Meissner in 1963. Yeah, Meissner's on the flatter regions of Newman, Unti, Tamburino generalized Schwarzschild solution. And
he says it explicitly?
Yeah, he explicitly says he invokes Hopf-Renow in the complete Riemannian case. Notes that in fact all you need for a certain version of Hopf-Renow is affine completeness, and then goes on to note that that the metric property fails in Lorentzian signature spacetimes, but the affine condition still holds, and so therefore affine incompleteness should be a marker of this kind of singularity. Second comment: it's not clear to me that we should think of Penrose's imposition of the Cauchy surface as a causality condition, because to the best of my knowledge, he was following Leray there, and Leray defined this global hyperbolicity almost purely topologically.
Yeah.
It wasn't really until Garroch proved the splitting theorem that I think people realized that this was really a causality condition. I'm not positive about that though. That's something I actually would really like to figure out.
Yeah.
But I'm pretty sure that at that point,
I think you're
it wasn't
probably,
thought of as a causality condition.
I would also have to look it up, but I think you're right that he followed Leray. And I'm not sure whether he, at the time, I mean, he didn't call it a causality condition, right? This way of schematizing it, that is actually from much, much later, right? In fact, the place the way I saw it, and also the argument that this is the structure of all singularity theorems that was pioneered in the 65 paper, and that this naming comes from a paper by Sinovilla. This actually would be very interesting because, I mean, quite quickly, the question of Cauchy hypersurfaces initial value formulation is turned into this, right, as something that is related to causality and whether you have a well-defined determinism. But whether that was already sort of in the air in 65 or 63 to 65, that would be very good to know. Yeah.
That's what I would really like to know, and I just don't know that.
The reason, I mean, as you saw on that slide, I underlined in blue almost everything apart from the Cauchy surface condition, because I felt that I really have to, dig in there and see how exactly that happened and how new it was at the time. And yeah.
So last comment, or no, the second last comment is on the energy condition. His use of the energy condition. So I can't recall now exactly how you phrased it, but one has to be a little careful because people had in fact used energy explicitly what is recognized by an energy condition.
Yeah.
Going back at least the earliest example I know of is Eddington's proof of a very restricted proof of the geodesic principle for dust. Where he explicitly uses what we would call the weak energy condition. He obviously didn't call it that, but he explicitly uses the weak energy condition for dust to show that dust follows geodesics, that you can derive that from covariant divergence free condition and what we call the weak energy condition. So people have been using it going back at least to the early 20s.
That's very interesting.
As far as I know, Penrose was really the first to use it in this very generic way. That was really radical.
Well, in a way, also Ray Chaduri and Koma also had something very close to, right? But also, as you say, not using it in that generic way, not employing it in this way, but clearly foreshadowing something there. But I think in a way, I'm also not sure whether, at least for Penrose, it's not primarily an energy condition, right? It's a focusing condition, right? Because it's all about how that condition, and he applies it to the Ricci tensor, right? It's only an energy condition if you apply it to the energy momentum tensor, but he uses it for the Ricci tensor, and then it leads to a focusing of the light rays, which then connects with the trapped surface condition to so
that's exactly right. But if I recall correctly, he does explicitly invoke the connection to the energy tensor to give it the physical interpretation.
Yeah,
if I remember.
That's true. I agree. Yeah, he mentions that, but then that's not what he uses, right? He uses it as applied to the Ricci tensor. Yeah.
And last remark is about Martin's remarks. I think Martin is absolutely right. But with regard to a rather small community, he's talking. I mean, he's talking about mathematical relativists who are focused on the initial value problem in mathematical relativity. It's an incredibly important community. They're doing extraordinary work, but it's a pretty small and somewhat insular community. I think if you look at people working in general relativity more generally, no pun intended, there's the incompleteness criterion is still very, very widely used. It's what's used in quantum gravity when people talk about singularity resolution. It's what's used, for instance, in Martin's own very, very beautiful singularity theorem. Mm-hmm. Unfortunately, he's not here, so I can call him out on his hypocrisy. But no, he's as far as I know, he's absolutely right about not only the fact that incompleteness doesn't play an important role in this mathematical relativity community, but he's also right in the more important point that the condition that these regularity conditions are concerned with, and whether dynamical evolution can be defined in these in these regions of low regularity, but that is a very subtle and very rich, both mathematically and conceptually, very rich notion of singular structure, a breakdown of something that is really worth, philosophers really should think about with regard to these issues. So now the question is, I mean, am I wrong? Is the Einstein argument, the argument Einstein gave to Hadamard, that's just a crappy argument. And I'm trying to be as charitable as possible, given, you know, the fact that the theory was what, like 8 years old at that point, and people were struggling with all these hard conceptual problems. But that's just a really crappy argument, because I mean, even looking at Schwarzschild's own original coordinates, it's like a one-line calculation to show that the bigger m gets, the smaller the density gets. So how could he possibly, for enormous m, like density can be arbitrarily close to 0? Like what was he thinking?
Well, I think that, I mean, first of all, I must say, again, this is sort of a, you know, somebody took lecture notes, right? And on that spot, it's really not much more than what I wrote there. So this is a twice reconstructed argument, right? So very far from a direct quote or anything, right? So who knows what he actually said and how well the guy wrote it down. But I mean, the crucial part was the final step, right? That the pressure becomes, the pressure tends to infinity. The denser the star gets, the quicker the pressure tends to infinity. And if the pressure tends to infinity, then that will affect the TT component of the metric and basically diverge, and then clocks, you know, if GTT is not working anymore, then clocks don't run anymore. And if clocks don't run anymore, that's still, you know, it's 1923, a very operational way of thinking about what it means for time to pass, right? If time doesn't pass anymore, then it can't contract further either, because it's a process in time. So that's a bit how it's done. It's a qualitative argument. And I think, he never wrote this down, right? He never published the argument. So he might have thought of it as very much on the fly, right, in answer to the discussion, and then quickly forgetting about it, because it might not have sounded like such a great idea to himself. But I liked it. But one of the reasons why I included it is because it has the, you know, well, first, it's the first time that the idea that, oh, maybe the event horizon could end up outside of the star, that question comes up there for the first time. So for that, you know, Hadamard, right? That's all credit to Hadamard. That's the first time. And I also liked it in terms of flow, because in a way what Einstein gives is an anti-singularity argument, right? That the singularity can never ever form in that way, at least the spherical singularity. And that is a nice counterpoint to the later Penrose singularity. Yeah.
Thank you.
Okay, next up is Sam, and then I'm going to let Tiffany jump in to ask something of her great questions in the chat, and then finally class.
Great. So I had 2 questions, but Eric, in his inimitable way, already asked one of them. So I'll just ask the other, and it relates back to kind of like something that one can see in the many different points of view that you presented, and also our earlier discussion with Martin, which has to do with the fact that in your historical presentation, Dennis, you've of course been very ecumenical about different interpretations of what these things mean. But as you see, like these are matters of sometimes heated dispute within different communities in relativity. I was hoping you could say, therefore, a little bit more, not just about how these different interpretations came about as possible different points of view that people have presented on how we should both represent mathematically singularities and physically interpret their significance, but also you might say like the dynamical interaction between advocates of these points of views, and how these lead to questions about the interpretation of general relativity more broadly, and the relationship of general relativity with other physical theories like quantum theory.
Yeah, well, okay. Well, I think about it. let me start in a way that helps me get to that. So I remember when I was working on the on Einstein's work on the problem of motion in the 1920s, and where he explicitly says, oh, I take basically singularities, they represent material particles. And I remember talking about this with Jim Weatherall at some point, and he was very shocked, dismissive, but clearly this doesn't make sense. Singularities don't even exist in the space-time, so this doesn't make any sense, this way of talking, right? I said, well, but it depends how you interpret it, right? I mean, and then that's how I then thought, I don't think he actually means that in any sort of philosophical way of representing the singularities represent particles. What he means is, well, we, for the purpose at hand, we have the singularity, we don't properly model the particle, we don't have the model, and that's all the singularity is. It's a placeholder for something that we haven't done yet, right? And I think that's a viable interpretation, both of Einstein's work on the Schwarzschild solution and the calculation of Mercury's perihelion, and of the problem of motion stuff. But I thought then, well, so does this still happen? And then when I started to look more at exact solution literature, so I think there's two really interesting complementary, but to some extent separate sub-communities in mathematical GR from the 1950s onwards. And one is the kind of, so people like Penrose, Hawking, Garrosh, who try to prove very general theorems about incompleteness, geodesics, and so on, and who really don't try to engage, or who try to prove theorems that apply to as many solutions as possible. So not getting bogged down by the properties of any one particular solution. But they also, of course, thereby make it so general that it's then not clear how it connects back to the particularly important physically relevant solutions, right? And then there's a different community which didn't really spend much time with these general theorems, but who instead try to find new exact solutions and try to use them in a physical way, right? And that was also something that happened, or that really took up steam from the late 1960s onwards. So especially, people obviously Kerr, Newman, Robinson, Troutman, and so on, huge classes of new exact solutions. And in those, both in the original papers, and even if you now look at exact solutions books, when you look at a particular solution like this, and people are so what could this solution possibly mean? You find these questions both in the original papers and in the textbooks on exact solutions. What could this solution possibly mean? Well, look, there's a ring singularity, or a curvature singularity, or a point singularity, or a directional singularity here in the solution. This could be a material source of the following type, or this could be an indicator. They use that word indicator quite a bit also. This could be an indicator of a material source that has the following form. Whether it actually is then something that you have to substantiate, right? You have to then try to find a model of the material source which you can asymptotically match to the previously found vacuum solution. So I think that's the context in which both, looking at exact solutions, trying to interpret them, and trying to apply them to particular physical systems, in which both the placeholder and the indicator interpretation, which are quite close to each other, originate. Versus some of the other interpretations originate in this trying to find more general theorems that cover huge parts of the solution space. And to some extent, I think it's also different temperaments, right? And people with different backgrounds. So people like Penrose and Garrosh, who were in many ways mathematicians first, and then started to work in GR, versus highly mathematically gifted theoretical physicists, right? Who worked on exact solutions, not so much on general theorems. Sorry, that was a long-winded answer, but I think so. I think basically the different interpretations originate because people want to do different things. So in some sense, also these interpretations become tools, just like a particular exact solution is a tool in order to describe a physical system, right? And I think that's something that in philosophy we sometimes lose sight of, that it's not always a question of which is the right or the true interpretation, but which interpretation is the best tool for a given purpose. Yeah.
Okay, Tiffany, if you want to.
Okay, thank you. And I think your last response there starts to get into some of the questions that I have that are more on like what were the stakes at the time in terms of a historical sense. So I had this question about how much should we consider Eddington's worldview on like his views on stellar collapse in general? You know, he butt heads with a lot of people in this regard, and how can we use that to discern more information about how he's thinking about singularities? The next question is, how does the rise of technology, particularly computing, and we're coming out of like the Manhattan Project, and there's a particular way of thinking about problems that the field of general relativity benefited from, and we can see that even happening later with Pretorius, who has to even define how the problems are solved based on the technology that's being utilized to solve those equations. And is there a different way of thinking, like pen and paper? Does that influence how one is interpreting this concept? And then the last question I had, just as a graduate student, very curious, like how can these debates be tracked beyond published papers and beyond conference proceedings? Because I wish we could be in the room at these very conferences just to see the ways of thinking and knowing and get a more sense of the societal implications. Thank you.
Great questions. Thank you very much. I'm afraid I don't have very good answers to them because that's questions that I want to know the answer to, but I haven't done it yet, right? I haven't done so say starting with the Eddington question. I think quite probably his theory of stellar structure has a huge influence on this, and quite possibly related to what Eric just said, right? That if you use a particular energy condition, like a weak energy condition, that makes immediate sense if you're working on stellar structure and you try to weigh different ways of modeling a star. You say, well, minimum condition is something that the energy is positive, and then you can work on from there. You can try this model and this model, but quite likely all models will have in common that they only have positive energy, right? So I think that will have had a huge influence. And how his view of singularities, I'm not sure yet how exactly it interacts. And part of it is that I haven't spent enough time yet with looking at his work on stellar structure. I think I've come to think basically exactly what you were putting your finger on, that there is probably a very strong interdependence on his opinions about singularities and his opinions about stars and his thoughts about stars. But I haven't nailed it down yet because I haven't studied everything he did on that. The second question was about computers. And yeah, so I think it definitely played a major role for Wheeler because, Wheeler was an important scientist, not on the both on the Manhattan Project, even though he wasn't at Los Alamos, but he was part of the overall effort. And I wouldn't be surprised at all if the fact that he had access to, really the best computers of the 1950s, right? Who had access to the best computers in the 1950s was because of that. I'm not sure how exactly it happened, whether it was sort of connections that he already had or whether he literally needed to use the kind of clearance that he had in order to get computing access. That would also be interesting to find out. And that's also something I want to look at in the near future. And Wheeler's, and that relates to your third question, Wheeler's estate is beautiful, also beautifully ordered. I mean, he has I think 30 notebooks just on, relativity notebooks, all numbered, all dated, with really detailed notes and files on, with people's names on them where he interconnects. So it's really quite a sophisticated paper database already. And so I've started to study the notebooks, but there's so much, just starting with the notebooks and, for example, looking at his Finkelstein file, looking at his Penrose file and so on. But the notebooks itself are so vast that it's just really a lot of time even to get an overview. So, and I think that, so that relates also to the third question. So in addition to published papers, there are, for some people, there are literary estates. And so the Corona got in the way, but I'm cooperating with Penrose to help him order his literary estate, so his papers, his correspondence, his drafts, and so on. And hopefully once it's possible again to travel from Germany to England, we'll keep doing that. And then obviously also talk to people, right? So like with him, he has an amazing memory. I mean, he remembers in detail things he did 50 years ago, even concrete mathematical steps. So in talking to him and recording those conversations, that's I think another pathway. Of course, one has to be very careful with question of how reliable is the memory. I mean, we know from studying Einstein's stuff that even so he finds the field equations in 1915, and then already in 1924 he writes his first account of how I found general relativity, right? So somebody asks him, okay, give us a historic account, how did it happen? And we see, or especially John Norton and Tilman Sauer, Jürgen Renn, John Stachel, and others have reconstructed and compared this to the original notes, right? So there also, fortunately, we had the Zurich notebook, so his notes while he was working on trying to find the Einstein equations. It's really quite different. I mean, what happened is really quite different, even to how he remembers it only 9 years ago, 9 years later. And that's when he's like 45 or so, and he already misremembers what he did 9 years before. So, but I think to these different sources, literary estate, talking to people when it's still possible, analyzing published papers, correspondence, it's a matter of using different sources and trying to find a coherent picture. But there's always, there will always be uncertainty left. Yeah. Thank you. Great questions.
Okay, Klaas, did you?
Yes, well, thank you very much. I'm sorry it's late. First, Dennis, thanks for this fantastic talk. It was a great afternoon you gave us. I have one very, very quick question and a slightly longer one, which I'll keep short. The quick one is, so you mentioned Reichenbecher, but I guess you mean Reichenbach, or was there a Reichenbecher?
Yeah. Yeah. It's quite an interesting figure, actually. Yeah. I mean,
you mean it was not Hans Reichenbach, it was a Reichenbecher.
I think Ernst Reichenbecher.
Aha, all right. Let's discuss that later. My serious question is, so as you pointed out correctly, it's left to the reader in Penrose's 1965 paper what the conclusion of the theorem is, but even the definition of a singular space-time as being causally geodesically complete is left to the reader. Yes. He never spells it out. And I looked just at his 1967 Battelle Rencontre lectures published in 1968, and it's similar. He never says this is a good definition. And as far as I know, it was Hawking in his Adams Prize essay from 1966 who made this point. This is a good definition of a singularity. And also in the Hawking and Ellis book, they spent a whole page discussing this. So would you agree that it was really Hawking who pulled the trigger?
I think, I mean, it was definitely, but not Penrose, who tried to give a definition of a singular space-time. I agree. I think it's interesting, and I think he held back because I think he didn't feel that was the way to go, to give such a definition. And you see, especially in the introduction of the 65 paper, he speaks about physical singularities and real singularities, and in other papers too, it very much looks as if he's trying to argue geodesic incompleteness is, well, I think is an indicator for a singularity in the old sense. So I think he was never really, I mean, even after Hawking proposed it, I think he was never really happy with the idea that one is not thinking anymore of, curvature singularities or physical or real singularities, but instead only of singular spacetimes, right? I mean, I think he thought, well, so fine, we're thinking about singular spacetimes, but in the end, we really want to know those singular spacetimes that have a singularity in the old sense. And we want to know what those singularities mean then.
All right, yeah, I saw Eric put Garroch in the chat. That was Garroch before the Adams Prize essay of 1966, or? Let's see.
Eric?
Yeah, I think so, because if you look at the received by date in the Garroch paper, it's something like July 19. It's something in like mid 1965.
Yeah, but then it's competitive because Hawking's thesis was also from 1965, which was the root of his Adams Prize essay. So it's so it was in the air. Interesting. Okay. Yeah.
I've actually heard from Bob Wald that the reason I'm confident in saying this is because Wald has told me that he specifically told me that Garroch was responsible for that.
All right.
And that Garroch actually gave Penrose a particular idea about how to prove a more general theorem. And that's something that I really want Dennis to ask, because I've asked Bob, and Bob, of course, being Bob, he says, "Oh, I don't remember, I have no idea," which is just so irritating. But so I would really love Dennis to ask Penrose this, to see if Penrose remembers, because when I say I asked Bob, I'm sorry, I meant I asked Bob Garroch, not Bob Wald. Yeah. Wald told me this. I tried to verify it with Garroch. Garroch said he didn't remember, which he always says about everything. And then, so I would like Dennis to ask Penrose.
Yes, and perhaps also Charles Misner, who was already mentioned. And Misner, as far as I know, is still alive and sharp. And I think he was earlier. That was about 63.
Oh, 63, yeah.
So I asked him, I don't think I sort of, I'll check my notes and the recordings, but I think I might have asked him a bit more generally, trying to basically reconstruct in those years, right, 58 to 65, what were the major influences. And the most important one he always mentions in a variety of interviews is Finkelstein's lecture.
Finkelstein.
Absolutely crucial. Then the discussions with Wheeler, right, especially, well, just focusing on the problem and relating it to gravitational collapse. And also with Misner. And because he was in Princeton in between 58 and 65 for a year. And Misner he mentioned more than once also for the time after 65. Garroch, at least he didn't, I'm pretty sure he never mentioned him as a crucial influence in those years. Oh, and Trautmann, in the sense that the idea of the trapped surface came up, or was triggered by him walking next to Trautmann. But sorry, Ivor Robinson. Mixed them up.
Robinson.
Yeah.
All right.
It's interesting that Garroch. So Garroch would have been. Where did he do his PhD in Chicago?
No, he did it with Wheeler.
With Wheeler in Princeton. Okay.
Yeah.
There's an interesting contrast about as striking as you can get between Einstein's and Wheeler's approaches. Einstein, going back all the way to his first papers, is avoiding detailed theories of matter, that in a way, special relativity, the quantum statistics, all of his work is always trying to do what he really makes into these heuristic arguments, which at the time was still a fairly new concept, at least the way he deployed it. Wheeler, from his earliest work, collaborating with Bohr, the liquid drop model, his early work on fission, work on the Manhattan Project, what kind of rods should be used in the reactors, then his work on the hydrogen bomb. The answer to Tiffany's question and your follow-on is absolutely. Wheeler used the same computers, the same techniques that he developed for modeling the hydrogen bomb, where he was working on the project at what was then the Forrestal campus next to Princeton off Route 1. And it had been a farm, then it had been used for testing chemical, biological agent, warfare agents. And then it was taken over and used for this ancillary part of the hydrogen bomb project, which was specifically around computer modeling of thermonuclear chains. So, in a way, Wheeler's exactly interested in pushing things as far towards a matter theory, nuclear reactions, and so on. And Einstein's all about avoiding those kinds of commitments. So they're just, and Oppenheimer is between the two. He runs the Manhattan Project, but he's also one of the more philosophically minded American physicists between 1900 and 1950. So he's an interesting and, as always, very complicated character.
Yeah, if I may, very briefly, I already put Kip Thorne's book in the chat, but also about Wheeler and exactly everything that Peter was just mentioning. Thorne relates all these things in a very nice way. I mean, the book is crazily called Black Holes and Time Warps, but it's a serious intellectual history of general relativity, mainly from the point of view of the Wheeler school, but much more generally. It's really a great book we should all read, I believe. Mm-hmm. And also especially about this stuff with the bomb and yeah.
It was called Project Matterhorn. Anyway.
Right.
Good. Well, we've kept you all a very long time over, and I want to thank the organizers, and especially the talk was just a real tour de force. Dennis, thank you for its extent and depth.
Thanks. Thank you. Thank you for the great questions and the discussion.
Thank you, Dennis.